the universe is only 13.8 billion years old. There has not been enough time since the Big Bang for gravity to pull together anything this massive. Yet we see it, stretching across 10% of the observable universe. We are going to explore the structure that broke cosmology. You will see how gamma-ray bursts exposed this impossible formation, why computer simulations cannot recreate it, and what happens when the rules of the universe stop making sense. If you are ready to question everything we thought we knew about cosmic structure, hit that like button and subscribe. Let us begin. In November 2013, a team of astronomers noticed something wrong with their gamma-ray data. These bursts of energy come from dying stars across the cosmos, each one marking where a massive stellar body collapsed. The researchers were mapping their locations to understand how galaxies spread through space. What they found made no sense. The gamma-ray bursts formed a pattern. They clustered together across a region so vast that it dwarfed everything astronomers had ever observed. Imagine looking at a map of your city and suddenly realizing all the buildings form a single continuous structure stretching from New York to Los Angeles. That gives you a fraction of the scale we are discussing. The structure measured approximately 10 billion light-years across. To put that in perspective, our entire Milky Way galaxy spans about 100,000 light-years. This formation was 100 million times wider than our galaxy. Light leaving one edge of this structure would take 10 billion years to reach the other side, traveling at 670 million miles per hour. The team ran their calculations again, then again. The pattern remained. They were looking at what appeared to be a connected wall of galaxy superclusters, each supercluster containing tens of thousands of galaxies, each galaxy containing hundreds of billions of stars. The math worked. The measurements were solid. The problem was different. According to the cosmological principle, the universe should be roughly uniform at large scales. Think of it like looking at an ocean from an airplane. Up close, you see individual waves, but zoom out far enough and the surface appears smooth and even. The universe should work the same way. Small variations close up, uniformity at cosmic distances. This structure violated that principle completely. It was confirmed through multiple independent observations using different detection methods. Scientists cross-referenced the gamma-ray burst data with optical telescopes and radio surveys. Everything pointed to the same conclusion. Something disorganized existed where randomness should dominate. The discovery team named it the Hercules Corona Borealis Great Wall. The name comes from its location in the sky, positioned between the constellations Hercules and Corona Borealis as viewed from Earth. But names were the least of their concerns. They had just found something that challenged nearly a century of cosmological theory. Here is where it gets stranger. The theoretical maximum size for any cosmic structure sits at about 1.2 billion light-years across. That number comes from decades of physics calculations about how fast gravity can work and how much time has passed since the Big Bang. Anything larger simply should not have had time to form, yet this wall measured 8 times that theoretical limit. The researchers published their findings knowing the backlash would come. Some astronomers questioned whether this was truly a single structure or just a statistical fluke. Others argued the gamma-ray bursts might be clustering by chance. But the data kept supporting the same conclusion. The probability of this pattern forming randomly was less than 1 in several thousand. Even more unsettling was what this meant for our understanding of cosmic evolution. If structures this massive can exist, then our models of how the universe developed after the Big Bang need serious revision. Every simulation, every equation, every prediction about large-scale cosmic architecture assumed nothing could grow this big. What could pull together that much matter over such distances? Gamma-ray bursts are the brightest electromagnetic events in the universe. When a star at least 20 times more massive than our closest star collapses into a black hole, it releases more energy in 10 seconds than our star will produce in its entire 10 billion year lifetime. These explosions shine so bright that we can detect them from the edge of the observable universe. Each burst acts like a cosmic lighthouse. It tells us exactly where a massive star died and, more importantly, when. Because light takes time to travel, seeing a gamma ray burst from 10 billion light-years away means we are watching an event that happened 10 billion years ago. The light has been traveling toward Earth all that time. Astronomers use these bursts, to map the ancient universe. By recording where each explosion occurs, they build a three-dimensional picture of how galaxies were distributed billions of years ago. It is like taking a photograph of the universe in its youth. Most of the time, these bursts scatter randomly across the sky. That is what the cosmological principle predicts. The Hercules Borealis Great Wall appeared when researchers plotted 283 gamma-ray bursts detected between 1997 and 2012. Instead of random distribution, they found clustering, intense clustering. The bursts formed a distinct line across one section of the sky, all occurring at roughly the same distance from Earth. This concentration suggested something massive occupied that region of space. Galaxy clusters tend to produce more stars, which means more supernovae, which means more gamma-ray bursts. Find a concentration of bursts, and you have likely found a concentration of galaxies. Simple enough in theory, but the concentration they observed stretched too far. The gamma-ray bursts mapped out a region spanning roughly 60 degrees across the sky. From our viewpoint on Earth, that is about 120 full moons placed side by side. Now remember, these bursts were all happening approximately 10 billion light-years away. Geometry tells us that something 60 degrees wide at that distance must be monumentally, impossibly large. The team used statistical analysis to confirm the clustering was real. They divided the sky into sections and counted how many gamma-ray bursts appeared in each one. The section containing the Great Wall had significantly more bursts than probability allowed. The odds of this happening by random chance measured at less than 1 in 2,000. Other research teams began checking the data independently. They used different statistical methods. They looked for errors in the original measurements. They cross-referenced the gamma-ray positions with surveys of galaxy distributions. Every analysis confirmed the same thing. The clustering was real. The structure existed. What makes gamma-ray bursts especially valuable for this kind of research is their brightness. We can see them across distances where galaxies become too faint to detect directly. They illuminate regions of the universe that would otherwise remain hidden. In this case, they revealed something we never expected to find. Something that had been sitting in our data for years, waiting for someone to look at the pattern instead of individual points. The cosmological principle states that the universe looks essentially the same in all directions when viewed at large enough scales. This idea forms the foundation of modern cosmology. Without it, our equations describing cosmic expansion stop working. Our models of the Big Bang collapse. Everything we think we understand about the universe falls apart. The principle emerged from observations made throughout the 20th century. Astronomers noticed that galaxies spread across space in a relatively uniform way. Sure, you get clusters here and there. You see voids where fewer galaxies exist. But step back far enough, and the average density of matter stays consistent. The universe has no center, no edge, no special direction. This uniformity comes with a built-in scale limit. Calculations show that structures in the universe should not exceed about 1.2 billion light-years across. That number derives from something called the particle horizon during the early universe. Essentially, it is the maximum distance over which matter could have influenced other matter in the time available since the Big Bang. Think of it like this. Gravity pulls matter together, but it moves at a finite speed. The universe is only 13.8 billion years old. There has only been so much time for gravity to do its work. Even if every particle of matter in a region started pulling on every other particle from the moment of the Big Bang, there is a mathematical limit to how large a structure they could build. The Hercules Borealis Great Wall exceeds that limit by a factor of 8. It is not just big, it is impossibly big, given the age of the universe and the speed at which gravity operates. Imagine trying to build a bridge, but you only have enough time to construct 100 feet of it before your deadline. Then someone points out your bridge is 800 feet long. Either your measurements are wrong, your timeline is wrong, or the laws of physics you are using do not apply. Scientists call this the horizon problem. Different regions of the universe should not be able to coordinate their behavior across distances larger than light could have traveled since the beginning of time. Yet here sits a structure that appears coordinated across 10 billion light-years. How did all that matter know to clump together in the same direction? Some physicists suggested the structure might have formed earlier than we think, during a period called cosmic inflation. Inflation theory proposes that the universe expanded exponentially fast in the first fraction of a second after the Big Bang. This expansion could have stretched quantum fluctuations into the seeds of large structures. But even inflation has limits. The mathematics of inflation predict structures should still cap out around that 1.2 billion light-year mark. The Great Wall sits far beyond what inflation can explain. It challenges the principle that the universe develops uniformly. It suggests that either our understanding of cosmic evolution is incomplete, or we are seeing something we have completely misinterpreted. Neither option provides comfort when you have spent decades believing you understood how the cosmos works. Picture our Milky Way galaxy floating in space. 100 billion stars spinning in a spiral disk about 100,000 light-years wide. That seems enormous from our perspective, standing on a small planet orbiting one average star near the outer edge. But in cosmic terms, the Milky Way is tiny. Now zoom out. Our galaxy belongs to a group called the Local Group, which contains about 80 galaxies clustered within 10 million light-years. The Local Group itself sits inside a larger structure called the Virgo Supercluster, a collection of galaxy groups spanning 110 million light-years. Superclusters represent some of the biggest structures astronomers recognized before 2013. The Hercules Borealis Great Wall contains thousands of superclusters. Imagine stacking the Virgo supercluster 90 times in a row. You still would not reach the size of the Great Wall. This structure makes our supercluster look like a single grain of sand on a beach that stretches for thousands of miles. Scientists measured the Great Wall using redshift, which tells us how far away objects are based on how much the universe has stretched their light. Light from the Great Wall has a redshift value between 1.6 and 2.1. Those numbers translate to a distance of roughly 10 billion light-years and an age of 10 billion years. We are seeing this structure as it existed when the universe was less than 4 billion years old. At that time in cosmic history, the universe was still relatively young. The first stars had formed. The first galaxies were coming together. But conventional theory says there had not been enough time for gravity to assemble anything approaching the scale of the Great Wall. Matter was still spreading out, still organizing into the structures we see today. Large-scale cosmic architecture was supposed to still be under construction. Yet the Great Wall was already there, already formed, already massive beyond theoretical limits. The structure contains an estimated 18 billion trillion stars. That number is so large it loses meaning. But try this comparison. If every star in the Great Wall represented $1, you would have enough money to give every person on Earth about $2.5 trillion each. And that still would not exhaust your supply. All those stars mean enormous amounts of mass. Mass means gravity. Gravity means the structure exerts influence over an incredibly vast region of space. Any galaxy wandering too close to the Great Wall gets pulled toward it, eventually joining the structure and making it even more massive. This feedback loop should have limits based on how fast gravity can work and how much time has passed. The Great Wall appears to have ignored those limits completely. Understanding the scale helps us grasp why this discovery shook cosmology. This is beyond an anomaly. This is beyond an outlier in the data. This is a fundamental challenge to our equations, our models, our entire framework for understanding how the universe grows and evolves over time. And it gets bigger when you look closer. When you point a telescope at the night sky and capture light from distant galaxies, you are not seeing those galaxies as they exist now. You are seeing them as they were when their light began its journey toward Earth. Light from a galaxy 1 million light-years away shows you that galaxy as it looked 1 million years ago. Light from 10 billion light-years away shows you 10 billion years into the past. This time delay gives astronomers a powerful tool. By observing objects at different distances, we can watch the universe evolve. We see galaxies forming in the early universe. We watch them merge and grow. We track how cosmic structures developed from the nearly uniform conditions after the Big Bang into the complex web of galaxies, clusters, and voids we observe today. The gamma-ray bursts that revealed the Great Wall occurred between 9 and 10 billion light-years from Earth. That means we are observing events that happened 9 to 10 billion years ago, when the universe was only about 4 billion years old. We are looking back through time to see a structure that had already formed while the cosmos was still in its developmental phase. Here is where the timeline becomes problematic. The Big Bang happened 13.8 billion years ago. In the first few 100 million years after that, the universe was too hot and dense for stable structures to form. Stars needed about 200 million years to appear. Galaxies took several 100 million years to coalesce. The universe needed time to cool, to expand, to allow gravity to pull matter together into organized structures. By the time we see the Great Wall, only about 3.8 billion years had passed since conditions became stable enough for large-scale structure formation to begin. That gives gravity 3.8 billion years to collect galaxies into superclusters and arrange those superclusters into a wall spanning 10 billion light-years. Standard physics says this is impossible. Gravity propagates at the speed of light. Even if two regions of space started pulling toward each other from the moment structure formation began, they could only influence each other across distances. Light could travel in 3.8 billion years. That limits structure size to about 3.8 billion light-years maximum. The Great Wall spans more than twice that distance. Some researchers propose the structure might have started forming even earlier, during the period immediately after the Big Bang, when quantum fluctuations could create tiny variations in matter density. These variations could act as seeds that gravity later enhanced into large structures. Computer simulations based on this idea consistently produce structures no larger than 1.2 billion light-years across. They never produce anything like the Great Wall. The timeline problem gets worse when you consider that the Great Wall is not just large, it is organized. The gamma-ray bursts show a clear linear pattern, suggesting the structure has a defined shape and orientation. Random gravitational collapse should produce more circular or irregular formations. This looks deliberate, which makes no sense because gravity does not have preferences or directions. Something about our understanding of cosmic evolution must be incomplete. Laszlo Balázs led the team that discovered the Great Wall. He is a Hungarian astronomer who specializes in gamma-ray burst research at the Konkoly Observatory. When his team first processed the data showing this massive clustering of bursts, Balázs assumed something had gone wrong with their analysis. The pattern was too strong, too organized, too large to be real. They checked their instruments. They reviewed their calculations. They looked for coding errors in the software they used to map the burst positions. Everything checked out. The gamma-ray bursts were clustering exactly where the measurements showed. The pattern was real. Balázs described the feeling as looking at something that should not exist. Imagine working on a puzzle and discovering a piece that is 8 times larger than the frame supposedly can hold. Either the piece is wrong, the frame is wrong, or your understanding of how puzzles work is fundamentally flawed. Those were the only options. The team spent months verifying their findings before publishing. They used statistical tests to measure how likely this clustering could occur by random chance. The tests came back showing odds of less than 1 in 2,000. In scientific terms, that is significant. In practical terms, that means if you repeated the history of the universe 2,000 times, this pattern might randomly appear once. Maybe. Other astronomers were skeptical when the paper first appeared. Skepticism is healthy in science. Extraordinary claims require extraordinary evidence. Several research groups set out to either confirm or debunk the discovery using independent datasets. They looked at optical surveys that mapped galaxy positions. They examined X-ray data from space telescopes. They analyzed radio observations from deep space. Every independent analysis confirmed the structure. The Great Wall was there. The measurements were accurate. The size calculations were correct. The cosmological problem was real. What made this particularly challenging for the astronomy community was that the Great Wall did not announce itself dramatically. There was no obvious visual signature in the sky. You could not point a telescope at a specific location and see a wall of galaxies spanning your field of view. The structure revealed itself only through careful statistical analysis of gamma-ray burst positions accumulated over 15 years. This meant the Great Wall had been hiding in plain sight in our data. Astronomers had been recording these gamma-ray bursts for years without realizing they were mapping something impossible. The bursts seemed random until someone stepped back and looked at the overall pattern. Only then did the structure emerge. Balazs noted in interviews that discoveries like this make you question what else might be hidden in astronomical data. If a structure this large could go unnoticed for over a decade, what other cosmic anomalies are we missing because we are not asking the right questions or looking at our observations from the right perspective? The Great Wall changed how astronomers approach large-scale cosmic mapping. Teams now specifically look for unexpected patterns and clustering at scales previously thought impossible, and they are finding things that suggest the Great Wall might not be alone. The theoretical size limit for cosmic structures comes from a concept called the homogeneity scale. This is the distance at which the universe should start looking uniform. Below this scale, you see clusters and voids. Above this scale, matter should be distributed evenly in all directions. Decades of observation and mathematical modeling placed this scale at approximately 1.2 billion light-years. That number is not arbitrary. It derives from the physics of cosmic expansion and gravity. When the universe was young, matter was distributed almost uniformly with only tiny variations in density. These variations were quantum fluctuations, stretched to cosmic scales by inflation. Over time, gravity amplified these fluctuations. Denser regions attracted more matter and became clusters. Less dense regions emptied out and became voids. But gravity needs time to work. It can only pull matter together at finite speeds. The universe has only existed for 13.8 billion years. That limits how large gravitationally bound structures can grow. Physics sets a firm boundary on structure size based on these constraints. The Great Wall is 8 times larger than that boundary. Several physicists have proposed modifications to explain this. One idea suggests that the early universe had larger quantum fluctuations than we currently think. Bigger initial variations would allow bigger final structures. The problem is, we can measure those early fluctuations by looking at the cosmic microwave background radiation. The measurements show fluctuations too small to produce anything like the Great Wall. Another proposal involves dark matter. We know dark matter exists because we can see its gravitational effects on galaxies and galaxy clusters. Dark matter makes up about 85% of all matter in the universe. Some researchers suggested that dark matter might clump differently than normal matter, creating larger structures faster. Simulations testing this idea still cap out at the 1.2 billion light-year limit. Dark matter helps, but does not solve the problem. A more radical idea questions whether gravity works the same way at cosmic scales as it does in our local region of space. Maybe the force of gravity gets slightly stronger over distances of billions of light-years. This would allow structures to form faster and grow larger than standard physics predicts. The challenge is that changing how gravity works has enormous consequences for all of cosmology. You cannot tweak one thing without affecting everything else. Some scientists went back to the data itself. They argued that the Great Wall might be a projection effect. Imagine looking at stars in the night sky. They appear to form patterns like constellations, but those patterns are illusions. The stars are at vastly different distances. They only look connected from our viewpoint. Maybe the gamma-ray bursts are doing the same thing, creating the illusion of a structure when they are actually scattered at different distances. This argument fell apart under scrutiny. The redshift measurements confirmed all the bursts occurred at approximately the same distance. They were not at different depths, creating a false pattern. They genuinely clustered together in 3-dimensional space. Every conventional explanation failed. The Great Wall violated the theoretical size limit because the theoretical limit assumed our models were complete. Apparently, they are not. Gravity is the weakest of the 4 fundamental forces in physics. Electromagnetic force is about 1 billion billion times stronger than gravity at atomic scales. Yet gravity dominates cosmic structure. It holds planets in orbit. It binds stars into galaxies. It pulls galaxies into clusters. At large scales, gravity is the only force that matters. This happens because gravity is always attractive and has infinite range. Electromagnetic force can push or pull, so opposite charges cancel out at large distances. Strong and weak nuclear forces only work at subatomic scales. Gravity affects all matter equally and never turns off. Over cosmic distances and timescales, gravity always wins. The strength of gravitational attraction depends on mass and distance. Double the mass and you double the pull. Double the distance and the pull drops to 1/4 strength. This inverse square relationship means gravity gets weaker rapidly as objects move apart. At cosmic scales, even though galaxies contain enormous mass, they sit so far apart that the gravitational force between them is incredibly weak. This weakness limits how fast structures can grow. When matter is spread thin across space, gravitational attraction between different regions is subtle. It takes billions of years for that gentle pull to draw enough matter together to form something like a galaxy cluster. Building something bigger requires even more time because the forces are even weaker across those larger distances. Computer simulations model this process by starting with the conditions of the early universe and letting gravity do its work. Researchers input the known amounts of normal matter and dark matter, apply the laws of gravity, and fast forward through cosmic history. These simulations recreate the universe we see remarkably well. They produce galaxies, clusters, superclusters, and voids that match observations. Except they never produce anything like the Great Wall. No matter how researchers adjust the initial conditions within observed limits, no matter what variations they introduce, the simulations consistently create structures that max out around 1.2 billion light-years. They have run thousands of simulations using different parameters. The results remain the same. Some researchers tried artificially boosting the strength of gravity in their simulations to see if stronger gravitational forces could produce larger structures faster. The answer is yes. If you make gravity about 3 times stronger than it actually is, you can get structures approaching the size of the Great Wall to form in the available time. But we know gravity is not 3 times stronger than we measure it to be. We have tested gravitational strength extensively at many different scales. The measurements are precise and consistent. This creates a logical problem. Gravity, as we measure it, cannot produce the Great Wall in the time available. Yet the Great Wall exists. Therefore, either our measurements are wrong, our understanding of how gravity operates at cosmic scales is incomplete, or something else besides gravity contributed to forming this structure. None of these options are comforting. The first suggests our entire framework of physics is off. The second requires rewriting general relativity. The third implies forces or effects we have not discovered yet, and there is still more that does not add up. The universe began 13.8 billion years ago with the Big Bang. We know this age precisely from multiple independent measurements. The cosmic microwave background radiation gives us one number. The expansion rate of the universe gives us another. The ages of the oldest stars give us a third. All these methods converge on the same age. The uncertainty is less than 1%. This timeline creates strict limits on what can exist. Nothing in the universe can be older than 13.8 billion years. Nothing can have formed before the conditions allowed stable matter to exist. Nothing can be larger than gravity could build in the time available. These are not theoretical constraints. They are observational facts based on physics we can measure and test. The Great Wall appears in our observations at a redshift, indicating we see it as it existed 10 billion years ago. That means it formed sometime in the first 3.8 billion years after the Big Bang. Remember, structure formation could not begin immediately. The early universe was too hot. Atoms could not form until about 380,000 years after the Big Bang. The first stars took 200 million years to appear. Galaxies needed several hundred million more years to assemble. Being generous, stable structure formation began around 500 million years after the Big Bang. That leaves approximately 3.3 billion years for the Great Wall to form before we observe it in our data. 3.3 billion years for gravity to pull together matter across 10 billion light-years of space and organize it into a coherent structure. Here is why that timeline is impossible. Even light traveling at its maximum speed of 670 million miles per hour can only cross 3.3 billion light-years in 3.3 billion years. That is the absolute fastest that any force or influence can propagate through space according to relativity. Gravity moves at the same speed as light. This means regions of the Great Wall, separated by more than 3.3 billion light-years, could not have influenced each other at all during the formation period. Think of it like trying to coordinate a construction project where your work crews cannot communicate with each other. They are too far apart for signals to reach between them in the time available. Yet somehow they all build parts of the same structure that perfectly connect. Either they coordinated before your time limit began, which is impossible because nothing existed then, or they are following some blueprint we cannot see. The standard model of cosmology has no mechanism for creating coordinated structures across distances where coordination should be impossible. Inflation solved a similar problem in the very early universe by suggesting distant regions were once close together before rapid expansion separated them. But inflation ended a tiny fraction of a second after the Big Bang. It cannot explain coordination on the time and distance scales of the Great Wall formation. Some scientists suggested we might be seeing multiple unrelated structures that happen to line up from our perspective. The statistical analysis rules this out. The probability of multiple structures randomly aligning this way is negligible. The timeline problem has no conventional solution. The Hercules Corona Borealis Great Wall was shocking, but it was not the first time astronomers found cosmic structures that challenged our size expectations. The history of discovering larger and larger formations shows a pattern. Each time we improve our ability to map the universe, we find something bigger than theory predicted. In 1989, astronomers Margaret Geller and John Huckra discovered what they called the Great Wall. This structure stretched about 500 million light-years across space, making it the largest known structure at that time. It consisted of superclusters and galaxy filaments arranged in a sheet-like formation. The discovery prompted questions about how something that large could form, but it still fell within theoretical limits. Scientists adjusted their models and moved on. Then in 2003, a team analyzing the Sloan Digital Sky Survey found something bigger. The Sloan Great Wall measured approximately 1.4 billion light-years across. This structure pushed right up against the theoretical maximum size limit. Some cosmologists began questioning whether that limit was real or just a guideline. The structure was enormous, but not quite impossible. It sat at the edge of what physics allowed. 2004 brought another surprise. Researchers identified a massive cosmic void called the Eridanus supervoid. This was not a structure made of matter, but rather a region with significantly less matter than surrounding areas. It spanned about 1 billion light-years. Large voids raise different questions than large structures, but they still challenge the cosmological principle. The universe should not have such dramatic variations in density at these scales. In 2007, astronomers found a grouping of quasars spanning 4 billion light-years. Quasars are actively feeding black holes in the centers of distant galaxies. Finding them clustered together was unexpected. Finding them clustered across 4 billion light-years was startling. This structure exceeded the theoretical limit by more than 3 times. However, some scientists argued it might be a chance alignment rather than a gravitationally bound structure. The debate continued. Then, in 2013, came the Hercules Corona Borealis Great Wall. At 10 billion light-years, it dwarfed everything found before. It was not sitting at the edge of theoretical limits. It was not questionably beyond them. It was definitively, undeniably, impossibly large by factors that could not be explained away by measurement error or statistical fluctuation. This progression suggests a troubling possibility. Maybe the theoretical size limit is not a real limit at all. Maybe it is just the point where our models break down because they are incomplete. Each new generation of telescopes and surveys reveals larger structures. Each discovery pushes further, beyond what we thought possible. The pattern implies we might not have seen the largest structures yet. We are limited by how far into space we can observe and how much sky we can survey in detail. There could be even larger formations waiting to be discovered in regions we have not mapped thoroughly, or farther away than our current instruments can detect clearly. If the Great Wall is not unique, if structures this size are common, then our entire understanding of how the universe organizes itself needs revision. The Sloan Great Wall held the record for largest cosmic structure for 10 years. Discovered using data from the Sloan Digital Sky Survey, it measured 1.4 billion light-years long. This placed it right at the theoretical maximum size that gravity should be able to produce in the time available since the Big Bang. Astronomers thought this might be the natural limit, the biggest thing the universe could build. The Sloan Great Wall sits about 1 billion light-years from Earth. We can see it more clearly than the Hercules Borealis Great Wall because it is closer and contains more luminous galaxies. Detailed surveys mapped its shape and structure. It appears as a massive sheet of galaxy clusters separated by voids, creating a foam-like pattern across space. Imagine bubble wrap at cosmic scale, with each bubble made of galaxy clusters. What made the Sloan Great Wall acceptable to cosmologists was its size. At 1.4 billion light-years, it pushed against theoretical limits, but did not break them. Researchers could explain its formation using known physics and slightly generous assumptions about early density fluctuations. The structure required everything to go right gravitationally, but it was possible, barely possible, but possible. After its discovery, cosmologists revised their expectations. They assumed 1.4 billion light-years represented the practical upper limit for cosmic structures. Anything larger would require physics we had not observed. Theoretical limits exist for a reason. They define the boundaries of what natural processes can achieve. Finding something at that boundary makes sense. Finding something far beyond it means your understanding is wrong. The Sloan Great Wall also confirmed that the universe organizes matter into a cosmic web. This web consists of filaments and sheets of galaxies surrounding enormous voids where few galaxies exist. The structure looks like a three-dimensional spiderweb, stretching across the universe. Gravity pulls matter into the densest filaments, leaving voids behind. This web structure appears throughout the observable universe at distances where we can map galaxy positions clearly. Computer simulations reproduce this cosmic web structure accurately when you input the right amounts of matter, and dark energy. The simulations show how tiny variations in the early universe grow into filaments and voids over billions of years. They match observations well. They predict the size and spacing of structures we actually see. They give cosmologists confidence that the underlying physics is correct. Those same simulations consistently fail to produce structures larger than about 1.2 billion light-years. Even when researchers adjust parameters within reasonable ranges, the simulations create cosmic webs with filaments and sheets that max out near the Sloan Great Wall size. This is why astronomers thought 1.4 billion light-years was the ceiling. Theory and observation agreed. Then the Hercules Borealis Great Wall appeared in the data. At 10 billion light-years, it was 7 times larger than the Sloan Great Wall. It was not slightly beyond theoretical limits. It was absurdly beyond them. If the Sloan Great Wall represented everything going perfectly right for structure formation, the Hercules Borealis Great Wall represented something fundamentally different, something that operates by rules we have not discovered. Dark matter changed everything in cosmology. We cannot see it directly. We cannot detect it with telescopes. We know it exists because galaxies rotate too fast to be held together by the gravity of visible matter alone. Stars at the edges of galaxies orbit at speeds that should fling them into space. They stay in orbit because invisible mass creates extra gravitational pull. That invisible mass is dark matter. Dark matter outweighs normal matter by about 5 to 1. For every atom of normal matter in the universe, there are 5 units of dark matter. This means most of the gravitational force shaping cosmic structure comes from matter we cannot see. Dark matter creates the scaffolding. Normal matter follows that scaffolding, lighting up the structure so we can observe it. Computer simulations show how this works. Start with the early universe filled with both types of matter distributed almost uniformly. Let gravity amplify small variations in density. Dark matter clumps together first because it only interacts through gravity. It ignores electromagnetic forces that would slow down normal matter. These dark matter clumps then pull normal matter toward them. Gas falls into the clumps, heats up, and eventually forms stars and galaxies. The result is a cosmic web where dark matter filaments connect galaxy clusters. The filaments act like highways. Galaxies move along them, merging and growing. The densest intersections in the web become massive galaxy clusters containing thousands of galaxies. Voids form in between where little matter exists. This picture explains the structure we observe throughout the universe. It also explains why structures have a size limit. Dark matter starts clumping early, but it still needs time to pull matter together across large distances. The clumps grow by consuming nearby matter and merging with other clumps. This process has a maximum speed determined by how fast matter can move and how much time has passed since the Big Bang. Even with dark matter helping, there is only so much structure you can build in 13.8 billion years. Simulations that include dark matter create realistic cosmic webs with structures up to about 1.2 billion light-years across. These simulations accurately reproduce the galaxy clusters, filaments, and voids we observe. The match between simulation and observation gives cosmologists confidence they understand large-scale structure formation. Dark matter is the key ingredient that makes it all work. Yet, those same simulations cannot produce the Hercules corona Borealis Great Wall. Researchers tried boosting the amount of dark matter. They tried making it clump faster. They tried giving it different properties within limits consistent with other observations. None of these modifications created structures approaching 10 billion light-years. The simulations stubbornly refused to build anything that large in the time available. This suggests dark matter scaffolding has limits just like normal gravity. You can only pull matter together so fast even when most of it is dark. The Great Wall exceeds those limits by such a wide margin that adjusting dark matter properties within reasonable ranges makes no difference. Something else must be involved. Or everything we think we know about how structure forms is missing a critical component. Not all astronomers agree the Hercules corona Borealis Great Wall is real. Some argue it represents a statistical coincidence rather than a physical structure. They point out that if you look at enough random data, patterns will emerge by pure chance. Deal enough card hands, and eventually you will get a royal flush. Map enough gamma-ray bursts, and eventually some of them will line up. This argument relies on probability. The universe contains billions of gamma-ray bursts. We have only detected and mapped thousands of them. If the observed clustering represents a tiny fraction of random bursts that happen to align, then there is no structure. Just a pattern that looks meaningful, but actually tells us nothing about how matter is distributed in space. The Discovery team addressed this criticism directly. They calculated the statistical significance of the clustering. Their analysis showed the probability of this pattern occurring randomly at less than 1 in 2,000. That is far below the threshold scientists typically use to confirm a discovery. In particle physics, researchers require odds of about 1 in 3.5 million before declaring a new particle discovered. But in astronomy, 1 in 2,000 is considered strong evidence. Other researchers repeated the statistical analysis using different methods. Some found slightly different probability values, but all confirmed the clustering was statistically significant. The gamma-ray bursts were concentrating in this region, far more than random chance would explain. This concentration indicated something physical occupied that space. The strongest evidence comes from cross-referencing. The gamma-ray bursts are not the only indication of structure in that region. Optical surveys that map galaxy positions show enhanced galaxy density along the same line of sight. Radio observations detect more activity in that area. X-ray data from galaxy clusters align with the burst positions. Multiple independent datasets point to the same conclusion. Matter concentrates there. Critics also questioned whether the structure is gravitationally bound. A true cosmic structure should be held together by gravity. The galaxies and clusters should be influencing each other gravitationally, moving together as a unit. Some researchers argued the Great Wall might be a projection effect, where unrelated structures at different distances appear connected from our viewpoint. This criticism is harder to dismiss completely. Measuring precise distances to individual galaxies in the Great Wall is difficult because they are so far away. The redshift measurements tell us approximate distances, but there is always some uncertainty. It is possible some of the galaxies are closer or farther than they appear, creating the illusion of a connected structure. However, the consistency of redshift values across the entire structure suggests otherwise. If this were random alignments of unrelated objects, we would expect to see more scatter in their distances. Instead, The measurements cluster tightly around the same redshift range. This indicates the galaxies genuinely occupy the same region of space, rather than being spread across different distances. The debate continues in astronomy literature. Some scientists remain unconvinced. They want more data, better measurements, additional confirmation before accepting a structure this large. But the weight of evidence increasingly supports that the Great Wall is real, and possibly not alone. Mapping the universe requires looking at it in 3 dimensions. When astronomers photograph the sky, they capture a 2-dimensional image showing where objects appear on the celestial sphere. This tells you the direction to a galaxy, but nothing about its distance. To build a 3-dimensional map, you need to measure how far away each galaxy sits. Distance measurements in astronomy rely primarily on redshift. When light travels through expanding space, its wavelength stretches. This stretching shifts the light toward the red end of the spectrum. The farther light travels, the more space expands during its journey, and the more the wavelength shifts. By measuring how much a galaxy's light has shifted, astronomers calculate its distance. This technique works because the universe is expanding uniformly. Galaxies farther away move away from us faster than nearby galaxies. The relationship between distance and speed is predictable and well tested. Measure the speed a galaxy recedes by measuring its redshift, and you can calculate its distance. This is how astronomers map large-scale cosmic structure. The gamma-ray bursts that revealed the Great Wall all showed redshifts between 1.6 and 2.1. These values translate to a distance of roughly 9 to 10 billion light-years. More importantly, they indicate all the bursts occurred at approximately the same distance from Earth. They were not scattered throughout space at different depths. They clustered together in 3-dimensional space, not just in our line of sight. 3-dimensional mapping reveals the cosmic web. When you plot millions of galaxies by their positions and distances, a pattern emerges. Galaxies concentrate along filaments that connect at massive clusters. Between the filaments sit voids containing few galaxies. The structure looks organic, almost biological, like neural networks in a brain or blood vessels in tissue. This web exists because matter follows the path of least resistance. Dense filaments form where gravity is strongest. Matter flows along these filaments toward the densest intersections. Voids form where initial matter density was below average. Once matter starts leaving a region, gravity accelerates the process. The void empties out as surrounding matter drains into adjacent filaments. The Hercules corona Borealis Great Wall appears as an unusually long and massive filament in this cosmic web. Instead of stretching a few hundred million light-years like typical filaments, it extends for 10 billion light-years. Instead of containing a few galaxy clusters, it contains thousands. It is not a different type of structure. It is the same type of structure scaled up beyond what should be possible. 3-dimensional mapping also reveals something unsettling. The Great Wall is not aligned randomly in space. It has a specific orientation relative to other large-scale structures in the observable universe. Some researchers noticed that several of the largest cosmic structures seem to align with each other, creating what looks like an axis through the observable universe. This alignment should not exist if the universe is truly uniform and isotropic as the cosmological principle requires. The more we map the universe in 3 dimensions, the more we find patterns that challenge our assumption of cosmic uniformity. Patterns that suggest the universe has structure, even on the largest scales we can observe. Cosmic filaments connect galaxy clusters like bridges connecting cities. These structures form naturally as gravity pulls matter along paths of maximum density. Early in the universe, matter was distributed almost uniformly, but tiny variations existed. Gravity amplified these variations over billions of years. Denser regions attracted more matter. Less dense regions lost matter to their surroundings. The result is a network where matter concentrates along lines, linking the densest points. Think of water flowing across uneven ground. It follows paths determined by the landscape, concentrating in channels that become streams and rivers. Cosmic filaments work similarly. Matter follows gravitational channels, creating dense streams of galaxies flowing between massive clusters. These filaments contain gas, dark matter, and galaxies. The gas inside filaments can reach temperatures of millions of degrees due to gravitational heating. When matter falls into a filament, it accelerates and collides with other matter already there. These collisions convert gravitational potential energy into heat. The heated gas glows in X-rays, allowing telescopes to map the filaments directly, even though most visible galaxies may be sparse. Measurements show typical filaments measure about 300 to 500 million light-years long and 10 to 50 million light-years wide. They connect galaxy clusters that contain hundreds to thousands of galaxies each. The matter within a filament is not stationary. Galaxies move along the filament toward the densest clusters at speeds of hundreds of miles per second. This movement represents matter continuing to organize itself into increasingly concentrated structures. The Hercules corona Borealis Great Wall dwarfs these typical filaments. If standard filaments are rivers, the Great Wall is an ocean current stretching across an entire planet. The scale difference is not just quantitative, it raises qualitative questions about how such a structure could form through the same gravitational processes that create normal filaments. Standard filaments form when matter collapses along one dimension while still expanding in the other two. Imagine a cloud of gas that starts pulling together. If it pulls together equally in all directions, it forms a sphere like a planet or star. If it pulls together along one axis faster than the others, it forms a filament. Computer simulations show this happens naturally when you start with the slight density variations observed in the early universe. But those simulations predict filaments should rarely exceed 500 million light-years in length. The Great Wall is 20 times longer. For it to form as a single filament, the initial density variation in the early universe would need to be 20 times larger and 20 times more extended than any variation we observe in the cosmic microwave background radiation. Those large variations would show up clearly in the temperature fluctuations of the background radiation. They are not there. Another possibility is that the Great Wall is not a single filament, but many shorter filaments aligned coincidentally. Statistical analysis makes this unlikely. The probability of multiple independent filaments lining up across 10 billion light-years is extremely small. Even if it happened, we would expect to see gaps between the segments. The gamma-ray burst data shows continuous clustering along the entire length. Cosmic filaments explain the smaller structures we observe throughout the universe. They fail to explain the Great Wall. The cosmological principle states that the universe is homogeneous and isotropic. Homogeneous means it has the same properties everywhere. Isotropic means it looks the same in all directions. These assumptions form the foundation of modern cosmology. Without them, Einstein's equations describing cosmic expansion have no unique solution. You cannot build a coherent model of the universe. This principle emerged from early 20th century observations. Astronomers noticed galaxies spreading uniformly across the sky. Later surveys confirmed this uniformity extended in all directions. Statistical analyses showed no preferred orientation or concentration. The universe appeared the same whether you looked toward Hercules, Orion, or any other constellation. This uniformity supported the idea that Earth occupies no special location in the cosmos. The cosmological principle allows for small-scale variations. Galaxies cluster. Clusters group into superclusters. Voids exist between structures, but these variations should average out when you examine large enough regions of space. By the time you look at scales of hundreds of millions of light-years, the universe should appear smooth and uniform.